dear participants. So today's session is divided into two parts. First part is from 7 to 7:50 for session 1 with a 10-minute breaks. Now next session from 8 to 8:50 and the last session from 9 to 9:30 for discussions. Now today's speaker is Dr. Anindo Bose, who is working as a senior scientific officer of Department of Physics of this University of Burdwan. He is working here for since 1996. He has done his MSc, MPhil and PhD from the University of Burdwan. He is an alumnus of International Space University, Strasbourg, France. He started his research career from National Physical Laboratory, New Delhi. He has received the Ursi Young Scientist Award. He is also a fellow of IET and also currently is a chairman of IET Burdwan Sub Center. He is also a member of URSI. He is also working as a consultant to various GNSS industrial organizations of India. His main research focus is in the area of GNSS, NavIC, low-cost GNSS NavIC-based applications, development and solutions. So with this introduction, I would request Dr. Anindo Bose to start his presentation. Sir.
Okay, thank you very much. Thank you very much, Jaydeep. I think I should, sorry, I should off my video so that will save some bandwidth for many of the participants who are participating using their mobile phones. Okay, so once again during discussion, I will come live in video. So let me start my presentation. Is it visible now?
Yes.
Okay. Okay. Thank you very much. Thank you very much. So my topic today is introduction to GNSS. As because myself and Jaydeep, we are handling the participants, the prints who are joining here and express their wish to participate here. I know the expertise and the level of the participants. Many of us present here are PG students from engineering colleges or subjects related to GIS. Some of them are mid-level scientists, and many of I know personally many of the participants they are advanced level GNSS researchers. So the second and third category, please forgive me. I want to put and say equal level playing field for those who are very new to the subject, right? So I want to start with what are the basics aspects of GNSS and why, as of today, it is a very important topic. Mostly, what are the operational principle, etc., etc. You have noticed that in week 1 we have basically kept the theoretical discussion so that step by step the participants go much deeper into the topic. So I will try to remain very simple and very easy so that everybody has the understanding of what is GNSS. So first of all, the disclaimer: the views and opinions what are expressed in this presentation are completely of mine and do not necessarily represent official policy or position of the University of Burdwan or any other agency for whom I'll be many of the names I will come across during my presentation. And second thing is some of the slides I've taken from Dr. Shweta Shah's presentation, who has shared her presentation today with me. And I thought it will be good to share, to take some of her ideas, blend into mine, that will be more interesting for the participants. Okay, so agenda today would be like that: navigation, the concept and implementation, so the global navigation satellite system segments, then the GNSS measurements and errors, GNSS positioning techniques and comparison, GNSS application, very important thing, the global GNSS business issues and future trends. So that will be the agenda I will try to cover in the next nearly 2 hours. So at 7:50, wherever we would be, I will stop there, take some questions, or in the meantime, and once again start at 8. I think it will be easy for everybody. So the fundamental problem in the nature is where I am, and we could see many examples in the nature where they're navigating. Take the case of this migratory bird. You know, in our university, if you come, probably you can see lots of migratory birds. And my friends from zoology department, they told me they comes from the bottom part of Siberia by classifying them. Well, so how every year, in many places in India, there are such places where this type of birds come migrated due to the huge winter there, very strong winter there. They come down to these places, and after some time they go back to their own habitat. So how come they can, even generation after generation? I have read on. You must have also read that there are many articles how they navigate. Similarly, many navigations are there, bird navigation techniques. They use sun as a compass, they use star as a compass, they use odor as compass. They have a magnetic map, what they can feel, and a magnetic compass to migrate from one place to another. Another interesting part where the picture is not there, that the bees, very small bees, they create their honeycombs in a place, and they can navigate to the flower or the bed of flowers. All the bees goes there, then takes the nectar and come back to the particular place. How do they navigate? So it's very interesting. So already there are means. Basically, subhuman species. There are many means through which they can navigate from one place to other. uh, so, for example, the underwater navigation techniques, basically they are based on Earth's magnetic field and navigation through sound waves. Right. So, I've taken this from Dr. Shah's presentation. I think she could have told it more on this one. This is a very good cartoon that the mother bird is teaching her children or the child how to navigate like that. So we have seen in case of tortoise or turtles, they navigate up to long distance. Even the fishes, they come to the very same place for laying their eggs like that. So already in the nature, the navigation is there, and a fundamental problem for human being also, to know where I am and to find out the exact directions in which I would move further. So those of you today who have gone back from your colleges or your universities or from your institutes, from the institute to your home, that you know that in which direction you should come out from the main gate and take which turn, and then which turn, and near to your home to follow which road. Obviously, you do not need the support from the Google map in your mobile phone to come back to your home at least. Okay. This is very essential. Just to imagine a very imaginary condition that we forgot how to go back to our home, or in a not so fine morning, I forget that how to go to Burdwan University for my stay place. So you can very well, though it seems very funny, but if you imagine, you will find that it's really, 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 I'd rather say survival tool. Okay. So the question comes for human being, for starting from if I go to the next slide, from prehistoric age, man wanted to know where I am and in which direction I should move. So our ancestors, who used to live in caves, they had to go out for hunting. So after hunting, when the sun was down, they had to come back to their caves. Otherwise, they would have been killed. So definitely, it was a survival tool for the art and science of navigation was a survival tool. So the question was, how to know my location precisely in any location at any point of time, and thirdly, everywhere on the surface of the earth, at least outdoors. That means when we are on the roads. How to navigate to the destination? We need guidance or navigation. So how far? So there are two routes. Which route is more convenient to save time and money and obviously fuel? That is very important. And the basic question is, where am I on the on the surface of the earth? And now you will understand that it is a very basic survival tool. Now coming back to this slide once again, early navigation used celestial bodies and landmarks. What we do today. So suppose going from one place to another, we search for landmarks, a big building or maybe a shopping mall or a sweet shop like that. We use those landmarks. And in the evening, uh, still now the celestial bodies are used. Where is the pole star? So that is the north direction. On the basis of that, we can find out east, west, north, and south like that. So still now landmark-based navigation, knowing okay, just now where you are, just in front of such and such cinema hall. I used to, or we used to call back to the calling party. So landmarks-based navigation still now is in operation. But the problem comes when there is no landmark. For example, we are in deep sea or ocean, or we are in the air. With the progress of the human civilization, obviously we came out from the land masses and went into this type of places where there is no landmark. So at that point of time, the celestial bodies used to help us. For example, the sun comes up from the east, or the pole star in the evening remains in the absolute north. But the problem becomes more intensified in a overcast day or during rainy season. And you must have heard or learnt about lots and lots and stories that in deep seas, the navigators and all the people inside a boat, they lost their bearing, they lost their direction, and ultimately, instead of going to the shore, they went more deep inside the sea. Their water and food were exhausted, and ultimately huge loss of human lives, and the precious materials they were carrying in their ship, they are completely destroyed. So eventually, next, the magnetic compass reduced the mankind's reliance on celestial navigation because it could properly show us what is the north direction. And on a map, if somebody knows his original location, uh, so one can start navigation to reach to a particular place. And you must be knowing that even today, inside cross country races, beside the driver's seat, there is a seat which is called the navigator's seat. The navigator is responsible for finding out the direction, the path to the destination. Obviously, in case of ships, they have got their own rather very precious place or important place. Then came sextant, which was developed and refined over several centuries, made Polaris, the pole star, and its celestial neighbors considerably more useful to navigators in high seas. Latitude of a point could be measured through measuring the elevation of pole star. During World War II, ground-based radio navigation system came into widespread use because of the other problems I told. So the examples are already I told that they used RF signal, radio frequency signal transmitted from a transmitter, and the candidates were radar. The other systems you may or may not have heard the DECA, Omega, LORAN, etc. Still now, LORAN, the long-range navigation, it is in use. But people understood that the electronic navigation I put into it quote is the real solution. Okay, so once again, so if I put everything together, so there are landmark based navigation, celestial based navigation, then came sensor based navigation using dead reckoning and other sensors like gyroscope, accelerometer, compass, odometer. The problem was complicated, errors accumulate quickly. Here, all the problems have been given. And then radio-based navigation, radar, LORAN, Omega, subject to radio interference, jamming, and they had limited coverage. That's the important thing. They have limited coverage. From the LORAN station, only maybe some 500 kilometers or 1,000 kilometers could be covered, not the whole region through which the ship is passing. So, just like in 1945, when Sir Arthur D. Clarke proposed that if we could place some satellites surrounding the Earth, three satellites, it could be used for point-to-point communication covering the whole Earth. People laughed at him. You must be knowing the story, or you can search for the story. Arthur C. Clarke, 1945 paper on satellite communication. You will appreciate that the real satellites came into existence and they were put into orbits in the late 50s. But in 1945, nearly 15 years ago, this science fiction writer, Sir Arthur C. Clarke, he proposed that. So once the satellite communication era came and people could understand the advantages of satellite, people thought, why not put the very same thing? Why not put the LoRa or Omega transmitters on board the satellites? And then started the satellite-based navigation or GNSS era. So the example, sir, I will talk more about it. The Transit, that was the first experimental system from US. Similarly, the Triskylon, Triskada were the systems which were developed by their Russian counterpart. And ultimately, the successful system was GPS. Everybody knows the name. Then the GLONASS, which was developed by Russia. Then the other major players, for example, the European Union developed the Galileo. The Chinese developed the Beidou, which is a global system. They have global coverage. The problem of what was talked earlier, that everywhere on the earth, it is now being solved by the satellite-based systems. And then came the QZSS from Japan and IRNSS or NavIC from India, which are regional systems. Now let us go to the concept of satellite-based navigation system. Believe me, I will try to remain as non-mathematical as possible for the simplicity and to start in a very simple way. So global navigation satellite system can provide highly precise. You may now start asking how precise. I will answer that. Myself and my colleagues will be answering that question. To have a feeling just now, from meter level to millimeter level. Believe me, up to uh, 2 to 5 millimeter level we can come down nowadays. That means just the tip of your ballpoint pen, we can so precisely find out our location. It's reliable. That means every time it gives the same solution. Location inform location, velocity, and time. So we call it position, velocity, and time, PVT, or in some cases it will call PNT, position, navigation, and time, at any point of the globe, anytime, using signals from satellites. So that is the basic definition. If you take it for the beginning. Now, how the system works? Basically, the system works on the concept of finding out our own distance from three known locations. For example, suppose we have a ball hanging from our ceiling fan. Now in the winter, the ceiling fan is not moving. For the Christmas, you have using a long string, you hung a ball. Now, from the floor, the if I tell you from the floor, the ball is say 3 feet high. From the right wall, it is 5 feet, and from the front wall, it is 7 feet. Now you know exactly where the ball is inside your room because we have given it three coordinates. Similarly, if I want to find out my location, what is x, y, z on the surface of the earth or very near to it. Why I'm telling very near to it, I will come to that later. Okay, so let my position coordinate be x, y, z with respect to the center of the earth, which is very basic trigonometry. So this is the center of the earth, 0, 0, 0, or let us take it O. On the surface of the earth, if we take this one to be the x-axis, this one to be the y-axis, and this one to be the z-axis, on the basis of that, so I am this much away in x-axis, this much away in y-axis, and this much away in z-axis. So if I can find out x, y, z, uh, I can find out my location on the surface of the earth. So any ship, if it can find out its own x, y, z, it knows what is its own location, right? But the thing is, if I tell XYZ with respect to the center of the earth, it is not comprehensible for most of the people because it will be some kilometers or meters. So let it take some 45001520 meter, 152 4500.1520 meter. Similarly, y a similar value and z a similar value. So I cannot find out where I am. But if I convert it in a more understandable parameter in the form of latitude, longitude, and altitude, what all the geography students they have picked up into their fifth or sixth grade, it is very clearly understandable for everybody. So what is done? First of all, calculate XYZ, convert XYZ into more understandable form of latitude, longitude, and altitude. Right. So now the question comes how to find out XYZ. For the process, already I told that using signals from satellite. So let us take, these are 4 satellites in sky. How they are put there, I will talk about later. So these are 4 satellites in the sky. Let us take it, these are GPS satellites. They are in medium Earth orbit, some 20,000 kilometers from the surface of the Earth. They are lying here. So if with respect to center of the earth, if the coordinate, if we measure the coordinate of this satellite, it would be x1 y1 z1, similarly x2 y2 z2. For it this is x3 y3 z3, and for this one it is x4 y4 z4, right? So by some means, there are many methods using which at any point of time we know what is the exact location of the satellite with respect to the center of the earth. Well, now what we're doing, if I take it here, we are trying to measure what is the distance between the satellite and myself, exactly my electronics, actually an antenna. So what is the distance between the satellite and my antenna? So we call it range or pseudo range. Why pseudo? Because it generally at the beginning will not give us the exact range. So if the r was up to this, it would have been range, but you can find out there is a distance of b between my point and a circle like that. Okay, so this is the distance ri. So we can write, now we can write an equation using basic trigonometry. So ri equal to distance between 2 points. So this is xi yi zi, or x3 y3 z3, and myself is xyz. So distance between 2 points, basic trigonometry tells Ri equal to, I stands for 1, 2, 3, 4, etc. Ri stands for xi minus x whole square plus yi minus y whole square plus zi minus z whole square whole root. So this is very basic trigonometry. So now I know, so I have created one equation, right? So how many unknowns are there? We have got 3 unknowns. As of now, we have got 3 unknowns, x, y, and z. So as because there are 3 unknowns, from basic algebra we know that to find out 3 basic unknowns, we need 3 equations, right? So 3 equations, so forget about this one now. So if we could have taken signal from this one, so we could have created 3 equations, r1 equal to x1 minus x whole square, etc., r2 equal to x2 minus x whole square, r3 equal to x3 minus x whole square, etc., whole root. But the problem comes on the left hand side, we have got a measurement, right? If I want to solve this equation, I have got these unknowns x, y, and z, and on the left hand side, we have got a measurement. We have measured the distance between the satellite and my antenna by some means. By some means. I'll come across to that one. So basically, that depends upon how precisely I can measure my time with respect to the satellite time. For example, to make it more simpler, suppose I drive my car at 30 kilometer per hour. Okay, so if I know for how much time I have driven, say 4 hours, I can calculate uh, uh, 30 kilometer per hour into 4 hours equal to 120 kilometer. So I have traveled 120 kilometers. So if I can measure the time of travel from of the signal from the satellite to my antenna and multiply it with the velocity of RF signal, which is the velocity of light, or c, 3 into 10 to the power 8 meter per second or 3 into 10 to the power 10 centimeter per second, obviously I can measure the distance. So measurement of distance need measurement of time. But the problem is when we want to measure the time of travel, we are depending on two separate clocks. For example, I want to measure the time of travel from my home to my office. So I use my watch at say 10:12. I have started at 10:23. I have reached there. So 10:12 minus 10:23 minus 10:12, that is the time of travel. So I can measure because I am using the very same watch for the measurement of the time. But here the RF signal starts from the satellite and the RF signals reach your receiver at a later time. Both of them has two different clocks, and in general any two different clocks, take an example, now take your clock and take your watch and maybe one wall clock in your home, you will find certain differences there. And in our case it's very important that in 1 second the RF signal moves 3 into 10 to the power 8 second. So we need to know the time at the order of 10 to the power minus 9, that is order of nanosecond, or better 10 to the power minus 12 second, that is picosecond order. So there is a mismatch between this time and this time. So if I know what is the time difference between the satellite and my clock, so the fourth unknown becomes the time difference between the satellite system and my receiver. That can be measured. So there comes the fourth unknown. So now we are with four unknowns: x, y, z, and delta t. That is the difference in time between the satellite system and your receiver. Okay. So there are four unknowns. For getting four unknowns, we take signal from four this type of satellites, write a set of four equations, and solve them using very complex algebraic method. And ultimately, we get XYZ. Whenever we get XYZ, from the XYZ, we convert it into latitude, longitude, and altitude so that everybody can understand. Now the question comes, so the basic requirement of getting geolocation, that means my own location using satellite system, is to simultaneously get at least four signals. I repeat, at least four signals, as because there are four unknowns. I need to write four equations, so I need to have at least four signals from four satellites. Now, how come I can get four satellites on the sky so that I can use their signals? The answer lies here. So the constellation, this is the constellation of GPS. They're so maintained that everywhere on the surface of Earth, there are at least four satellites overhead so that they can use them. Or this is a constellation structure for GLONASS. The satellites are placed in 3 orbits. Here the satellites are placed in 6 orbits. I think other people will talk more about this. I will give the basic flavor. Now, any GNSS satellite GNSS system is subdivided into three major parts. That is the space segment where the satellites are. We can do nothing with them. Next, the control segment. Once again, the broadcast signals, the controls. This is the control segment. The system developers, they receive the signal, checks for their validity, and if any correction is needed, they upload it here. And we remain in the user segment. As the user of GNSS, we will access the signal, get our location, and use it for different applications. So to give you some idea, I have selected the GPS space segment. It has been prepared by one of our students, Mr. Shukaboda. You will meet him using analytical graphics software. It's a very good tool which is free for the education community. You can create. This is the how the constellation looks like, and this is the ground track of the satellites. So we have created from Hyderabad on one particular day how many satellites are visible overhead. So overhead you can see 1, 2, 3, 4, 5, 6, 7, 8, 9. So nearly 9 satellites. On the average, we get 8 to 11 GPS satellites at any point of time overhead from India, from any point. So 6 equally spaced orbits, it's not very important. Each plane contains 4 slots. So 4 into 6, 24 satellites is the baseline constellation, that the basic constellation. In 2011, they extended it to 24 satellite slot. So let there be always redundancies. Okay, sorry, but it will not know why due to this. Okay. I do not know why it's working. So just to give you a different flavor, it's a three. You can see three orbit constellation. Earlier we had a six orbit constellation. Now it is a three orbit constellation, and everywhere instead of four there are eight satellites. So this bright dots are the satellites. So once again from Hyderabad you can see nearly six to seven GLONASS satellites. They can be visible. Okay. Now if you come to the NavIC or IRNSS space segment, I wanted to show this one as because the constellation pattern is completely different. That's why I wanted to give you a different type of flavor. In case of NavIC, it's a regional system. It do not cover the whole world, unlike what we have in case of GPS, GLONASS, Galileo, or Baidu. It covers. I'll come about the coverage, but the satellites, instead of being placed in a medium Earth orbit, the satellites are placed in uh, geostationary Earth orbit. Most of the people know about it, or geosynchronous orbit (GSO). Their height is nearly double of the MEO, nearly 40,000 kilometers from the surface of the Earth. Okay, so from Hyderabad, so you can see 1, 2, 3, 4, 5, 6, 7. It's a 7 satellite constellation. Earlier I told GPS is a 24 satellite, then 27 satellite constellation. GLONASS is a 24 satellite constellation. That's why they have got global coverage. And NavIC, it's a uh, regional system. So it has only 7 satellites so that it can cater the need of this particular region. And 4 are in inclined GSO and 3 are in GEO. And their constellation structure is completely different in comparison to the GPS or GLONASS or Galileo. So to have some more idea about the NavIC or IRNSS footprint and coverage, so this is where we are located. So this is India. So these are where the satellites are placed. So this one, and this one, they are. So this, and this, they are placed in geostationary Earth orbit, and this four in a complementary IGSO, inclined GSO, they are placed at 55 degrees east and 111.75 degrees east. So the primary coverage area, what is planned, that it would be 1,500 kilometer from the geographical boundary of India. Well, so from geographical boundary of India, so this is the central or primary service region, and the extended service region. So you can see the red dots here. So this is the extended service region, where the PBT solution quality is not confirmed that good as would be provided here. So but the interesting point is, you can see, so the African countries, East African countries, they will have one NavIC satellite always on their top, because this is GSO, so they will not move much. Similarly, the very densely populated areas of the Far East countries, they would have IRSS 1G on their on the zenith, near zenith. So it has got certain advantages. What are the advantages? I'll come. But before that, the multi-GNSS scenario. So now we have got the global constellation GPS from US, the GLONASS. It is GLONASS is developed by the Russians. The Galileo, it is developed by the European Union. The BDS or BEDU, it is developed by the Chinese counterpart. And the regional constellation QZSS and NavIC, already I told. And along with that, there are different types of augmentation systems. Augmentation system, uh, there would be different types of errors which will play. I will just touch upon it, which will play when the GNSS system will operate. To get rid of those problems, many countries, they have developed their own augmentation system. For example, wide area augmentation system, WAS. Sorry, it should be WAS. Then MSAS, it is developed by Japan. IGNOS, IGNOS is a very popular augmentation system developed by Japan. SDCM, it's developed by Russia. Then BDS bus, that is developed by the Chinese. KASS, the Koreans now in the process of developing their own satellite-based navigation system and their augmentation system. And in our case, Gagan, GPS-based geo-augmented navigation system. Basically, all these systems don't mix IRNSS or NavIC with Gagan. IRNSS is an independent system. Gagan is a system which supports GPS. So the GPS users in our country, they have got some problem. The problem is taken care of by the SBUS or Gagan. So now you can very well understand so many countries, along with Koreans, the people from the Arabian countries, they are trying to develop their own navigation system. I think in some of your mind, this question must be ringing. Why so many players? Why so many players? Why so many satellites? Why so many systems? Because putting satellites 24, 27, or take it to be 7 satellites in the constellation in the sky, it's a very costly business. Why so many people or so many countries, they're trying to put their satellite system into the sky, spending a lot of money? I ask you the question. I'll answer afterwards. So, what is the current scenario? The current scenario is, if we take all the systems together, there would be nearly 135 satellites in the sky. So 29 plus 24, 22 plus 44. In case of Compass or Bedu, it is much more number of satellites. In case of Japan, it's 4 satellites, and in our case, it's 6 satellites. Currently, we are having 5 satellites. So nearly 135 satellites, they're moving around us, around the Earth, for providing us the navigation service. So the question still remains the same. Why so many players spending a lot of money? Now, I want to draw your kind attention to this particular fact, that we are situated here in a very typical geographic location. Some time ago, nearly 20, some 10 years ago, a particular agency, what is called the Multi-GNSS Asia, that is a concern developed, that is a satellite navigation concern developed by the Japan Space Exploration Agency, JAXA. Actually, they predicted that in the region, you can see the red region, lots of satellites would be visible together when all of them would be fully operational. And currently, I forgot to tell, all the systems are currently operational. There is no developing or under development stage. Everybody is now operating. Now, what we got? This is the simulation. And we got, in 2019, we have not changed it, from Western India, we are getting 54 satellites. So our requirement was getting 4 satellites. Now we are getting 54 satellites. From Eastern India, that is our place, once again, we are getting 54 satellites. So on an average, over the whole country, as because of our typical geographic location, over the whole country, nearly around 45 to 50 satellites would be available, right? So we started with a problem that we need 4 satellites. Now we are in a problem that we have got 45 satellites, whom to use or whom not. And the other question is, how good we can utilize this typical scenario. This typical scenario of so many satellite systems. And in most of the cases, we are getting the signals free of cost. Question is, the associated issue is, not only we can have a very good technology, a combination of hardware and software, very equipped persons who can use this for the research purposes, but the main underlying point is how good we can use this technology for the benefit of the people of India, for the benefit of agriculture, for the benefit of transportation, for the benefit of surveying, for the benefit of fishing, etc., what not. So that's why we planned about this particular course, that how we can apply, sitting from India, how we can use this multi-GNSS environment and the advantage of India for the benefit of our countrymen. So I will stop in the first part after showing this one. So NavIC or IRNSS is our own system. It gives us several advantages over the other systems. First example, signals from high elevation angle over the service region. Why? In many cases, we have seen the lower parts are obstructed, maybe due to trees or buildings. And it is our study, and we published a few papers that during some time, even if we have got nearly 50 satellites, there are no satellites at the, for example, you can see here, above 60-degree elevation angle. That means from horizon, if you take a angle of 60 degree, above that there is no satellite. Now take the case. Above 60-degree elevation angle, there is no satellite. And below 30-degree, all the satellite signals are blocked by, say, you are in a narrow road or inside a forest, and the signals are blocked. So what will happen? We have got only a handful of satellites, maybe less than 4 satellites, and we will not be able to navigate or use GNSS. But as because NavIC is in very high altitude or in very high height in the GU or GSO, so their presence always will be around 50 to 55-degree, always from India. So it ensures the use of GNSS, say using GPS or NavIC together, GPS plus NavIC, GLONASS plus NavIC, Galileo plus NavIC. It ensures never that problem of uh, not getting enough satellites would be there. So next is S-band signal. So earlier this S-band signal was not there in any system. It has got its own advantage. For example, this type of atmospheric disturbances in L-band, the atmospheric disturbances, you can understand the red line is much more higher, where in the S-band, the red line is much lower. So S-band gives us some advantages, including it cannot be jammed because ready-made jammers are not available in S-band. Third, it has got a alert message service. During the rather offline program, we will discuss upon this one. We have developed a hardware software ensemble uh, uh, for getting alert message service for the fishermen. And thirdly, advantages in atmospheric research. I think two very eminent experts in the field. One of them is Dr. Dashora, and second is Dr. Dash from IIT Indore. They will be talking on this one. So they're the best persons to talk about this one. So GNSS signal and frequency allocation for the time being. I will not go detail into this one because this is not required at the point. Afterwards, as time will require, we will discuss this one. Uh, so these are the GNSS control segment. So these are the points from where the signals are received by GPS authority and the quality is checked and any correction is made. Similarly, this is the GLONASS, this is the Galileo control segments scattered all over the globe. In our case, scattered all over the country. These are the control segment and proposed outside Indian soil. The proposed center is in Novosibirsk in Siberia. In turn, GLONASS would have one control center in Bangalore. These are the GNSS user segment. Lots and lots of discussion would happen on this one. So different types of receivers, survey grade, etc., etc. And we will concentrate mainly on this one, the very low cost compact GNSS receiver, which are the game changers. So okay, so I stop here and the break. It is 1956. We will once again come back at 2:20:05. Okay, so till then. So take some rest. If you have any question, throw in the questions in the chat box or in the WhatsApp group. I hope you have lots of questions and I will be able to answer some of them and keep them for the other experts to answer. So for the time being, right